Hi, in this video we are going to talk about the simulated annealing algorithm focusing on the traveling salesman problem. So we will have a private single tour. It's going to be a reference to the best solution. Okay, then we will have a public void, for example, simulation, not a good name but whatever. In this case I'm not going to define a constants class in order to store the maximum temperature, the minimum temperature, the cooling rate and so on. I'm just going to define it here. So we will have a double temperature is equal to, for example, 10,000. Then we will have a cooling rate is going to be 0.03, whatever. Then we will have a single tour at the beginning. It's going to be the current tour is equal to a new single tour. Because we call the constructor without any parameter, it's going to be called. Okay. Sorry for this, not the current single tour, but the current solution. It's going to be a better name. So we have the current solution. Then we are going to generate some individual, basically. It's going to iterate through the cities in the repository. We are going to define some cities. We are going to insert it into the repository, and the generate individual is going to iterate through the repository cities, and it's going to add the cities from the repository to this list we have instantiated here, and we are going to shuffle it. So we have reorder it randomly. Let's save it. Okay, then we are going to print out that the initial solution distance is equal to the current solution dot get distance. Then we are going to initialize the best to be equal to a new single tour, and we set the best solution to be equal to the current one. So current solution dot get tour. And while the temperature is greater than 1, we are just going to generate a single tour. Basically a new solution is equal to a new single tour, and we just have to initialize it with the current solution dot get tour. Because we have specified some constructor parameter, this is what's going to be called. Okay. So we have a new solution, and we have to decide with the help of simulated annealing whether we are going to accept that new solution or not. And the algorithm is going to generate two random indices. So we are going to pick two cities at random, and we are going to swap them in the sense that, for example, we have this single tour. Okay, we have the cities A, C, D, E, I, J, H, G, F, B, and back to the starting point. The simulated annealing is going to pick two cities at random. The first city, for example, is going to be picked at random, for example, city C. We generate another city at random, for example, city E, and we swap them. So we have to swap them in the tour because it's going to be the new solution. It may be a better solution, so this is why we generate these random indices, and this is why we swap them. What does it mean that we swap them? That instead of visiting C at the beginning, we are going to swap it with E. So we are going to visit E. Then we visit D, and then after D, we are not going to visit E, of course, we are going to visit C, then I. Okay, so this is how we swap basically the edges. It's going to be a valid solution, of course, because we visit every single city exactly once, and it's going to be a closed cycle in the sense that we are going to end up with the same city from where we have started. We have just swapped the position of two cities at random in the tour. So this is why we are going to generate a random index, so an integer random generate random index 1 is going to be just fine. It's going to be an integer, and the new solution dot get tour size times the math dot random. It's going to generate a random index for the city in the range 0 and the number of cities in that given tour. Okay, then we get this city. So the city 1 is equal to the new solution dot get city. This is why we have implemented these helper methods and random index 1. Then we are going to do the same for the, I'm going to copy and paste it, sorry. It's going to be the same, but for the random index 2 is going to be another randomly generated city. And we get random index 2, it's going to be the city 2. And then we have to swap them. So the new solution dot set city, I think we have some method set city. New solution is a single tour, and the single tour has generated, yeah, we have a private, okay, sorry for that, it has to be public void set city. Okay, so we set the city, and basically we just have to swap them. So the random index 2 is going to be the city 1, and the new solution dot set city at the random index 1 is going to be the city 2. This is how we swap them in order to generate a new solution. Then we calculate the current energy is equal to the current solution dot get distance. So basically in this case, the energy is not going to be the function value as in the previous video, and I think it's going to be a double. Then we have the new energy, so the neighbor energy is equal to the new solution dot get distance, because we are able to decide what's the better solution according to the distance. The smaller the distance, the better the solution. We are going to have an acceptance probability. Okay, maybe with camel casing is going to be a bit better. With the current energy, then we have the neighbor energy, then we have the temperature. If it's going to be greater than the math.random, we are going to accept it. So the current solution, sorry for that, is equal to a new single tour, and with the new solution dot get tour. Okay, and then if the current solution dot get distance is smaller than the best solution dot get distance, of course we have to update the best. So the best is going to be equal to a new single tour, and we have to specify the current solution dot get tour. And at the end, of course, we have to decrement the temperature. So the temperature is equal to the, sorry for that, star equal to the 1 minus the cooling rate. And of course, we have to define this acceptance probability. It's going to be exactly the same as we have defined in the previous section. If the neighbor energy is smaller than the current energy, it means that we would like to accept this step with 1 probability, so with 100%. And anyways, we just want to return with an exponential function, the current energy minus the neighbor energy divided by the temperature. Okay. And that's all about the simulated annealing applied to traveling salesman problem. We have to make some basically mutations in the sense that we have to swap the two cities. This is how we generate a new solution. We have to swap them. We have to calculate the energies, so the current energy and the neighbor energy, which is the distance of the new solution. The distance is going to be a determining factor. If a tour has a very, very huge distance, it's not going to be the solution. Then if we are able to accept it, then we update the current solution, update the best solution, and we decrease the temperature. And why do we have to specify this acceptance probability? So why do we accept bad moves? Because these bad moves is going to make sure that we are going to end up approximately with the global optimum. Okay, so this is what's going to help to avoid local optimum. Okay, so that's all about the simulated annealing algorithm. In the next video, we are going to test it. Thanks for watching.